Well, good evening. I'm Scott Hauser. I am interim department head of economics and business. And welcome to our first research-focused alumni chat. So this is an outgrowth of our alumni chat we had in the spring that focused mostly on our programs and things that were going on in kind of the academic life of the department. And what we didn't get to spend enough time on is talking about the exciting research that's going on in the department. And so some of you who were here in April asked about research, and we decided to have another alumni chat that could focus just exclusively on research. And because this is the first one, we decided to give really the 30,000-foot view of research in economics and business. So what we're going to hear is several presentations from faculty and PhD students that are each going to last about 5 minutes. And if you have questions as we're going through those, please use the Q&A feature down at the bottom of what I hope is available at the bottom of your screen. And please let us know what questions you're interested in. We're just going to go through the overview presentations as quickly as we can, generate some sense of the exciting research that's going on in economics and business, and then we'll have some time for questions at the end. So please use the Q&A function. If the chat is working better for you, I'll keep looking in on the chat as well. And so we're going to begin as you would expect with research in EB with Professor Rod Eggert. So I'm going to turn things over to Rod, and I'll talk to you in a little bit.
Thank you, Scott. Can you hear me?
Yes.
All right. Well, thank you, and welcome everyone. I'm Rod Eggert. I've been here since 1986, so I'm the old timer in the group. As I think many of you know, my focus is especially on the markets and economic analysis of minerals and materials and related public policies, so mineral economics and public policy. I'm also deputy director of something called the Critical Materials Institute, which has been the foundation for most of the research that I've done over the last decade. And Scott, if you could advance my slide, please. The Critical Materials Institute, of which I'm the deputy director, is a research consortium funded by the U.S. Department of Energy. And this research consortium is focused on accelerating innovation that will assure supply chains for materials that the Department of Energy is prioritizing. And so it's things like rare earths for permanent magnets for the most efficient electric motors. It's various battery materials for batteries and energy storage. It's a number of minor byproduct metals used in electronic materials for photovoltaics and power electronics and similar things. This is a consortium that consists of several U.S. national laboratories, universities, and companies. You see the team members of CMI here at the bottom, and quite appropriately, Colorado School of Mines is right in the middle of the set of logos. Now, most of the research in the consortium is science and engineering, but at Colorado School of Mines, we lead the economic analysis, or the economic and supply chain analysis that informs the strategic and operational decision-making at a project level that the scientists and engineers do. And Scott, if I could have the next slide, please. And so, selected examples of recent work with graduate students. We've done work that asks what are the prospects for the long run availability of copper, important obviously for electricity and electrification, and lithium as a battery material. On the demand side, we've carried out studies related to better understanding the role of prices compared to technical considerations in substitution, specifically in rare earth permanent magnets and in lithium ion and other battery materials. We do something called criticality assessment, which is really a prioritization of materials that should be a focus of the Department of Energy research. We've done research related to trying to better understand what determines relative metal prices and the role that physical characteristics such as average crustal abundance of elements and the energy requirements in production play in determining relative metal prices. And as a last example, we've done work on price volatility. Students that I've worked with over the last few years have gone to work in a variety of places, including the private sector, investment banking, and LaVista Energy, a startup energy storage company, U.S. National Laboratories, Nrel, and Argonne National Laboratory, the Minerals Information Group at the U.S. Geological Survey, and academic positions at the University of Chile and the University of Alaska. And with that, I will turn it over to Tule Flamand. Thank you for your attention. Happy to discuss this further in the Q&A.
Thank you very much, Rod. So my name is Tule Flamand. I'm an assistant professor in economics and business. And my expertise lies on business analytics applications, which converts raw business data into meaningful managerial insights and decisions using data analytics. And we are trying to understand what is going on and what can happen. And we can use the outputs of data analytics into mathematical modeling, optimization models to prescribe optimal decisions that would maximize or minimize the objective of business problems. So given that business analytics can be applied to any areas where one needs to make decisions, for that reason, I have applications on many different areas. So I have researched with my colleagues and outside collaborators on retail analytics, text analytics, mining operations. I also have research on finding great solution methodologies to be able to handle computational challenges of solving these problems. I also have research with PhD students on sports analytics, renewable energy, European natural gas supply chain, and illicit gold supply chains. And today I will just, as an example, talk about sports analytics research that I've been doing with my student for team building decisions. And here the motivation is professional teams can gain this strategic advantage by utilizing data analytics plus optimization. And the question is, general managers of teams must decide how they value the players and then what kind of strategy they can develop to find the best combination of players for their team to bring the most value. And here, value we are considering is in terms of the ability of winning a game. So the main goal is here to build a balanced team according to team roles. So we wouldn't want to have only superstars in our team. And we also consider all the restrictions, limitations of the league. And we are specifically considering it in a professional basketball setting. So here the main contribution, for example, is combining this data analytics and optimization to be able to decide which college players to draft for our team, which players we need to trade among other teams, and which free agents we need to acquire. And so to do that, we first utilize predictive models. To do that, we are first setting up predictive model to assign values to college players who have not played in the league before. And we also assign these college players to different archetypes. Archetypes are different groups of players with different characteristics that we propose in a separate research. And we also consider how we can quantify synergy among players, and we are doing it on an archetype level. So to be able to look at synergy between two players, we are looking at which archetypes they belong to, and we use that synergy. We consider it because maybe two players can do great individually, but if they are not having a good synergy, they can bring a good value to the team. And we are using all these analysis into an optimization model to be able to prescribe optimal decisions for this team building problem. And we specifically examine an MBA case for this team building problem. And right now, the ongoing research on this, for example, reformulating this optimization model, because so far the research I mentioned is looking at the problem from only one team's perspective, but we need to also consider other teams' decisions, since that will affect the eligibility of players to be selected for our team. So we are considering it as a network model where nodes represent different teams or group of free agents, and arcs represent different acquisition activities among these teams and group of free agents and draftees. And we are considering this problem in a game theoretical approach. So thank you very much. And our next speaker is Dr. Jared Carbone.
Thanks, Tulay. Hi, everyone. Thanks for joining us. My name is Jared Carbone. I'm an associate professor at Mines, and I'm an economist who focuses on energy and environmental policy issues. Next slide, please. And specifically, I focus on economy-wide analysis using these computer simulations that are called computable general equilibrium models. And the key idea there is that they model the interactions between different industries, labor markets, capital markets, international trade linkages, and so forth. So I'm going to give you some examples of some of the current projects that I'm working on in this domain. Next slide, please. The first one is on jobs and environmental regulations. This is work that is supported by the U.S. Environmental Protection Agency, and was the outgrowth of a special advisory panel that I was on, advising the EPA on best practices using these economy-wide models. And one of the key things that came out of the report that we sent to the head administrator of the EPA was that we needed to do a better job of figuring out how labor markets and employment respond to the introduction of new environmental regulations. And this is really topical right now with the Biden administration getting set to advance its objectives on a number of fronts in environmental policy. So the idea here was to use economy-wide models to trace out how a shock in the form of a new environmental regulation in some sectors of the economy, like fossil energy sectors, might change jobs in those sectors, and also how workers of different characteristics in terms of past job experience and where they are in the work life cycle transition to jobs in other sectors or into retirement or unemployment. Next slide, please. Second application of these ideas, this is work funded by the Department of Energy, is looking at how climate change is going to affect where people decide to live in the continental United States in the future when the impacts of climate change set in, and use that to predict changes in the regional distribution of population across different parts of the country. So we developed a model that allows us to predict migration patterns across states in the US as part of that analysis. And the map over there on the right is showing you the sort of the biggest migration flows predicted for one of the climate scenarios that we consider in and out of Colorado. Next slide. Last piece of research that I'll mention here is a collaboration with researchers at Nrel, the National Renewable Energy Lab. A number of the PhD students that I've worked with here in the MEE program have gone on to find employment at Nrel, and they really make up a substantial amount of the economic modeling that goes on at the lab these days. So this is work focused on developing new modeling capabilities to do sort of regional economic analysis that's scalable in terms of geographic scale, sectoral scale, and is also linkable with a lot of the really detailed technical energy systems models that are housed at Nrel. So that's ongoing work as well. And I have other projects as well. Hannah Cayman, one of our PhD students, is going to talk about some other work later in the program. So thanks very much. I'm going to pass things off to Stephen Smith.
Here I am.
There you are.
Thank you. Once I did remote control, I couldn't control my mute or unmute anymore. So I just had an issue. Anyways, I'm Stephen Smith, assistant professor here at Department of Economics and Business. I also have some affiliation with the Hydrological and Science Engineering group because a lot of my resource work revolves around water. In addition to that, I'm also approaching these problems often through sort of the lens of property rights, sort of recognizing that these things shape sort of how we decide who owns what they can do with it. And ultimately that filters up into the decisions how we allocate those resources. And then last, because of that, I also dabble in some economic history simply because there's a long sort of experience of opportunities to look at different examples of policies that we can learn to affect contemporary policy as well. Just 3 quick examples on that. First one here was funded by the USDA. A lot of my time is spent thinking about agriculture simply because 80% of the water is used in that field, in that area. So this one looked at sort of groundwater because largely this is open access, basically a common pool resource. And so we wanted to see as people face scarcity, how they're dealing with it. And so we were looking in San Luis Valley where they pumped fine for a while. And then during a 2002 drought really hit this unsustainable withdrawal of their aquifer. And so they were innovative. They set a pumping fee, basically charging themselves for this water. And so this was very new and we want to see how this worked. So we looked down in San Luis Valley, looked at the 2 different areas here to see what had happened. And the punchline is that it was effective. We were looking at sort of this change in pumping. And sure enough, they reduced their pumping about 1/3 compared to the outside group. And so this seems like a promising policy tool that might be utilized elsewhere dealing with similar issues. Flipping is just showing sort of how history can be useful for these resource questions. This paper is really about looking at how policy uncertainty can affect your investment decisions, particularly when you've got a big investment that has a lot of fixed costs and it can't be used elsewhere. So this is about irrigation. Here we're looking at Montana, where we're using the Pacific Northwest land grants, the railroad, as a tool to look at that uncertainty. So basically, to subsidize these railroads back in the 1860s, the government gave away 15 million acres in Montana, going out 50 miles to both sides of this railroad. Every other sort of square mile went to the railroad, but they missed their deadline. And so for 15 years, it wasn't clear if I bought from the railroad or if I bought from the US government, which title was going to be valid. And so we used sort of irrigation as a thing to look at because it had this nice feature here of a spatial feature that we could look across the border. And sure enough, once that uncertainty showed up, we saw this reduction in investments in irrigation within that uncertainty. So it held up the Montana economy by about 25%. Right? So we can think about how that can affect uncertainty within states, regulatory environmental policy today. Finally, I'm also interested in looking at some water utility issues. And so this is looking at Denver Water as they're trying to balance this need to deal with conservation. So send a price signal to reduce that heavy use, but at the same time recognizing that water is an essential good that we need to provide at an affordable rate. So often we see these increasing block tier structures where the more you use, the more expensive it's going to be. Their innovation is that they're pushing to make a budget so that every individual person has their own budget based on their winter consumption. This has been good for conservation. Other cities have shown this. We're looking at sort of other issues, including the fact that you're going to be paying different amounts. So if you look at this, two people using the same water might be paying different amounts for that same water. So we want to see who that is. It turns out this does help larger households. It is progressive in the sense that richer areas, more homeowner areas are the ones more likely to be paying higher prices. I'll skip that. Newest research that you'll see a little bit later from students. I think there's a really fascinating story with irrigation moving east. It's historically been sort of a Western phenomenon, but we see it uptake there. That's it's basically 1978. We plateaued with irrigated acres in the West, but it's continued to grow in the east portion of the US. Meanwhile, there's not a lot of regulation or rules there, and it's now about 1/3 of our irrigated acreage. I think that's an area. And then also we'll see sort of how irrigation and renewable wind energy can interact. So I'll leave it there and turn it over to Michael Healy.
Thank you, Stephen. I'm not sure I have control of the slides yet, Scott. Okay, thanks. As Stephen said, I'm Michael Healy. I'm an associate professor on the business side of the department, and I also have the pleasure of directing the engineering and technology management program. Sorry, I don't know what's going on. It's going forward and backwards. What I'd like to do this evening is give you a quick overview of two research projects that I'm currently conducting. The first is focused on developing an autonomous control system for water treatment technologies, and there's a collaboration with Zahi Kath in civil and environmental engineering, Chris Villas at Oak Ridge National Labs, and Mandy Herring at Baylor. And then the second is research looking at characterizing the attributes of a firm's patent portfolio and what relationship different types of portfolios have on firm values. And this research is with Tulay Flamand, who you've already heard from, Sharon Matusik at CU Boulder, and Jeff Colvin at Indiana University. So one of the challenges currently with water treatment facilities is to realize operating efficiencies, you need significant scale. And so this first project is focused on developing a control system that can be used to operate much smaller systems at high performance and efficiency. The idea basically is to have an autonomous, adaptive, smart control system that will be able to make operating decisions in real time about what types and scale of treatments are needed to achieve water quality target objectives. And I think legally, I have to say this project is supported by the National Association for Water Alliance, which is a DOE research hub. As a test bed to develop the control system, we're going to use the direct potable reuse system that was developed by Zahi Kath's research group to treat feed from a conventional water treatment plant and produce potable water. The system is housed in a portable trailer and has a treatment train of pre-filtration and 6 advanced water treatment processes, and can basically produce 7,000 gallons a day of water at different target qualities. So if we look inside the trailer, basically we have this treatment train that has pre-filtration, ozonation, bath, ceramic microfiltration, GAC, UV, AOP, and then finally disinfection. And then we have a control system, we have a sensor network that has over 25 sensors measuring a variety of operating parameters and water quality. And the idea is to take this technical information and develop a control system that's combined with the economic information about the cost and benefits of the different treatment options to achieve specific water quality objectives as efficiently as possible. And so ideally, at the end, you'll be able to sort of have a control system that you can put sort of model different fit for purpose scenarios. You want a certain target water and what is the appropriate treatment train combination to achieve that target as efficiently as possible. The second project is focused on understanding the attributes of a firm's patent portfolio and what relationship these different attributes have to the amount of value that firms can appropriate from their innovations. As we all know, firms protect valuable innovations using portfolios of patents. Basically, they surround their core innovation with thickets of patents. However, prior research, when it sort of looks at firm-level patent metrics, simply aggregates individual patent metrics. So basically, you can think about an obvious metric would be counting the number of individual patents to the firm level. And this really ignores the reality of the way that firms use patents to protect their core innovations. As I mentioned, you've got sort of a thicket of related patents. And so a key challenge is to assess the distance between the patents and ideally distinguish between close patents that might be part of the same group protecting a core technology versus distant patents that have no sort of relationship. And so what we're doing to assess the distance is using information contained in patent claims and also the abstract, and using natural language processing algorithms to compute various distance measures between the pair of patents. And then once we have a good distance measure, we can create a dissimilarity matrix for different sets of patents to characterize the technology space and basically explore questions like, when does it make sense to use a dense or versus a porous thicket to protect innovations? Is it easy to capture value from the center or the borders of technology space? And can we sort of look at the overlap between firm portfolios to develop new measures of technological competitiveness? So now I'll turn it over to Ben Gilbert. Thank you.
Thanks, Michael. Okay, I'm Ben Gilbert. I'm an assistant professor here in the Economics and Business Division. I'm going to be talking tonight about the economics of flaring and methane emissions. And I'm working with this team of collaborators from mines and other institutions on trying to design incentives to reduce methane emissions and flaring, and also to analyze the constraints in the system that drive these activities. So why methane and flaring? Well, methane is a much more potent greenhouse gas than carbon dioxide over a 20-year time horizon. So if we can get a handle on these emissions now, then that buys us time for deeper decarbonization activities later. Flaring is itself a very large emitter of methane. So in site surveys, you often find that flaring is one of the largest point sources of methane. So it's important to study as well. And so what are we interested in this study I'm talking about tonight? Well, a lot of times, we think that a lot of the flaring and methane comes from these sort of upstream production sites. But in order to get to market, the natural gas has to go from the well through a gathering system of smaller pipelines, through the processing system, and then through these longer range transmission pipelines. So constraints or congestion at any one of those points along the supply chain can prevent the gas from getting to market. So what I'm going to show you tonight is I'm going to focus on the transmission pipelines and their effect on upstream flaring. But our team is working on looking at these other constraint points as well, and also looking at bringing in methane emissions data, because that's sort of the much more socially costly piece of this. Okay, so what do we do in the study I'm going to show you tonight? Well, we have daily data on interstate gas pipeline capacity utilization out of the Permian Basin, as well as unplanned pipeline maintenance events on those interstate pipelines. And then we don't have data on the intrastate pipelines. So we use the price spread between the local trading hub in the Permian and the Henry Hub in Louisiana as a measure of sort of overall transportation system congestion. And we combine all that daily data with daily flaring observations from the VIIRS satellite that is put out by the Earth Observation Group here at Mines. And then we're working on combining that data with other infrastructure data, and also working with faculty in the math and statistics department here at Mines to look at remotely sensed methane data. And we put all this data into a system of dynamic supply and demand equations for gas transportation services. So rather than think about supply and demand of the commodity itself, we're looking at the demand for the transportation of the commodity. And we run this model separately under days when the pipelines are congested versus when they're uncongested. So you can think about shifting supply as being these pipeline maintenance events when some capacity is taken out of commission. and shifting demand as being the capacity utilization data, or these price spreads that measure congestion. And if we observe flaring and methane emissions, you can think about that as excess demand for the transportation system. So if we take an initial look at the data that we have, on the left here, you can see that as pipeline capacity utilization increases, there's a flat to decreasing relationship with flaring in the Permian Basin until you hit about 80% of the capacity utilization, and then it starts to become an increasing relationship. Okay, so then once we put this into our dynamic supply and demand model, what we find is that the impact of an unexpected demand shock for interstate transmission capacity reduces flaring on days when those pipelines are not congested. That makes sense, right? Because people need the pipeline capacity, they put the gas in the pipelines. But on days when the pipelines are congested, these demand shocks actually increase flaring, and that flaring lasts for about 2 weeks after the demand shock date. When we look at demand shocks, not just for interstate transmission capacity, but for the entire transportation system, we find that it doesn't matter whether the interstate pipelines are congested or not. So as long as there is some point of congestion in the transportation system somewhere, that could be in the intrastate pipeline system, you're going to get flaring. Okay, and so then when we look at the impact of the unexpected supply shocks, so these maintenance events that bring some pipeline capacity offline, we find that the impact is much smaller, although it is slightly larger and statistically detectable on these congested days. So the big takeaway here is that these transmission constraints really matter a lot for the extent of flaring that's happening upstream. So all these graphs that I showed you imply that eliminating transmission constraints would reduce flaring by about half. So the next steps that we're doing is try to bring in the methane data and see if these results extend to methane emissions as well. And if they do, that presents society with kind of a big dilemma, because if we want to expand pipeline capacity to reduce these methane emissions, we're going to end up using natural gas for much longer into the future, and that's going to delay decarbonization. But if we don't expand the capacity, we're going to continue to endure methane emissions, which is going to accelerate warming. So with that, I'll turn it over to Ian Lang.
Hi, my name is Ian. I'm director of the Mineral and Energy Economics program. I'm also, I guess now, the third longest serving tenure track faculty member after Rod and Michael. So as sort of the wily vet that I've become, I kind of see a lot of needs for, being a utility player. The university is expanding its interdisciplinary research, and it's looking for people in a lot of different ways. And so sometimes you have to put on, your mining economics hat and talk about what's going to go on in space. And sometimes you put on your oil and gas hat and you talk about, how you can help fossil fuel dependent or fossil fuel producing communities. And so in a lot of ways, except I'm kind of the utility player, the Swiss Army knife of research. Generally try to use data analytics or econometrics. And these are just an example of some of the things that I'm working on with other folk at the university. Something that I'm sort of, a little more personally excited about is I always like to think a little bit about maybe more nuanced or, harder to initially see as impact, but I'm really interested in credit availability and how might households alter their energy decision-making given the amount of credit that's available. Generally, I've been doing this with sort of large regulatory changes in access to credit. So in the mid-'80s, states sort of sequentially started to deregulate their banking sector, and that they allowed extra branches or more than one branch from a bank within their state. And what we find as people sort of expand credit, because you now have to sort of compete for your customers. You have more than one branch within a state. We find that low-income households are more able to buy energy-using durable goods. They're able to buy dishwashers, clothes dryers, and things like that, and perhaps buy them more often. And this would affect the energy use in their household. The other thing that I haven't shown here, but we also sort of find, is that they're less likely to respond to government surveys that say that their house is too cold because they can't afford to turn on, their heat or heat their house high enough. And so our belief is that there's lots of areas where credit availability really restricts households' ability to make better energy decisions. With some undergrad students, we're working on, thinking about fossil fuel producing communities and what will happen as we move forward and they have, say, the energy transition moves away from fossil fuel. And so we have a current economics undergraduate student who's also one of the first fellowships through the university named Lauren, who's from Moffat County, so obviously very interested in this issue. And so, sort of to explain to her some possible policies that the government has thought up in the past and things that we might be able to do to help these areas. And so one of the things that came about were place-based investments, specifically looking at the opportunity zone tax credits. And so Lauren's working on research using data from the quarterly census of employment and wages to see how sectoral employment shrinks or expands as a result of being eligible for these opportunity zone tax cuts. Essentially, if you take some capital gains that you have yet to actually get, you can put them into these opportunity zone funds and you will delay / reduce your tax liability as long as you put them in these areas. And so, that's one possible way to help fossil fuel dependent communities to encourage investment into that area. The last thing I was just going to talk about quickly here is, right, so you may have been given emails or seen things on the webpage that Mines is starting this Global Energy Futures Initiative. Lots of excitement about that, obviously also with the Payne Institute. And so they were looking for somebody to help, lead a project on what is going to be the mineral demands as we move forward in the energy transition. And so we're working with some current mineral and energy economics students to make pretty graphs like the one down here that show how different mineral demands will increase if we were to follow, say, the International Energy Agency's, 2-degree energy technology, prediction for the future. So this is just, one example of how our work on the economics and business side is being used by the rest of campus and hopefully to help folk make better decisions. So I'm also, as director of the Mineral and Energy Economics program, here to also introduce the PhD students that we will have presenting. We have some seasoned vets like Yus, who recently presented her research to the Critical Materials Institute's annual meeting, and of course performed like a pro because she's presented many times. And then we have a lot of up and coming rookies like Hannah, who had her first presentation in the MEE department on Friday and did a smashing job. Now, in addition to our current PhD students who are here a little bit about, I just want to make sure that folk are aware. So we had I think the first time ever, we had a PhD student win the Rath Award, which is the university's award for the sort of dissertation that's going to have the biggest impact on society. This was in spring of 21. This is Emilio Castillo, who's now working in Chile. TC Agogo, who graduated, I think, in 2018 and at first went to Nrel, has recently been seconded to DOE to lead their response to the Biden administration's supply chain review. So she's coordinating all of DOE's activities within the supply chain review going on right now. Stepping back a little further, David Rajinovich has sort of led up the Federal Reserve of Kansas City's research on how sea level rise is affecting housing prices. And he discussed that work in the recent energy showcase that the Federal Reserve of KC in Dallas put on. And, we can go on, and there are folk like Steve Dahlke and Brett Jordan and Jacqueline Pless doing fantastic things with research that I'm happy to discuss more if anyone is interested in the specifics around there. But with that, I will relinquish control of the screen and hand it over to Hannah Gergen.
Hi, sorry, can everyone hear me? My name's Hannah Gagarin, and I'm a fourth year PhD student. And I'm just going to present a little something on a project I'm working on with Dr. Gilbert. Our project essentially focuses on how energy development impacts economic outcomes for communities in the United States. And we focus on a period from 2000 to 2015. So the focus of our project is to essentially assess how individuals and firms that are close to a wind turbine or a wind plant are impacted by that wind plant development in terms of employment and income, in terms of the number of employees that a business has or the wages that a business pays. There is a growing literature on economic outcomes for communities that experience energy development, but these studies use publicly available data, and that data is typically aggregated to the county level. So with that in mind, our project sort of diverges from the current literature because we have access to data at the individual level. And we do that because we have a partnership with the US Census Bureau. So essentially the census provides us with access to proprietary information about economic incomes at the individual level. So it's incredibly detailed data, and it's on employment history, your employment status, the wages, your income, all sorts of interesting stuff like that. And it's at the individual level. So it hasn't been aggregated to the county level or the state level, like in publicly available data. And so what we do is we combine this with energy facility information that's provided to us from Lawrence Berkeley Labs, and they're providing funding for us. And so we combine that information, and then we measure how individuals and businesses fare when there is wind development in their community. And so another great thing about this partnership that we have with the US Census is that having access to such detailed data, we can apply that to different energy developments. So we're currently looking at wind, but we could also look at solar, we could look at oil and gas developments, we could look at manufacturing sectors. So it's really rich for a lot of different potential studies in the future. So going back to this particular project though, we're essentially answering two parallel questions. If we focus on economic outcomes at the household level or the individual level. And then we also focus on economic outcomes for firms or businesses up to 100 miles around a wind turbine or a wind plant. So this project is important because we are using this really detailed data, which is really rich, and we're able to produce really detailed analysis when it comes to thinking about these economic outcomes. And that's really valuable because it's a more holistic view in terms of thinking about how energy developments impact communities. But another contribution that sort of makes our contribution twofold is that it allows us to compare our results with current literature that is aggregated to the county level. And that helps us better understand any potential biases that do come from using that publicly available data. So it helps other researchers, it helps the census sort of think about how they collect data and how they use it. Oops, sorry. So this is just a really like a sneak peek of our results. And this is just kind of like a sample. So this one just focuses on the Midwest region, and the motivation for showing this is really just that our data sets are so large that takes up a lot of computing power to do all the states that we're looking at. So it's easier just to sort of look at a slice. So there's a lot of numbers on here, but a big takeaway here is that our current results are 3 times larger than what's currently in the literature. So that's pretty profound. If you look at this first column here, the annual earnings column, you can see that for each additional megawatt of wind capacity within 100 miles of a worker is associated with an earnings increase of about 50 cents. That seems pretty small, but when you take into account the amount of workers that are within that 100-mile radius, that's over $3 million annual increase in earnings. So that is actually pretty significant. So just take those results with a grain of salt because we haven't adjusted for a lot of things yet. They're very preliminary. So we do need to correct for endogeneity and then include things like instrumental variables and other treatment variables and stuff. But we definitely will continue working on this in the future. And we plan to eventually expand this study to the rest of our states, not just the Midwest, and then also compare analysis with county level results. And I'm just going to hand this off to Shivani.
Hi, everyone. I'm Shivani Mathur, a fourth-year PhD candidate at, I have the control. I'm Shivani Mathur, a fourth-year PhD candidate in the Mineral and Energy Economics program. I am currently located in Ketchikan, Alaska, and really excited to be part of this chat. I have a background in engineering, public policy, and economics, and I previously worked with nonprofits in India and the National Renewable Energy Lab. Okay, yeah, sorry. So today I will focus my presentation on research I will be conducting through my PhD program while pursuing a DOE fellowship, which is in the coming year 2022. The fellowship is funded by the Department of Energy, and it is part of the Solar Energy Innovators Program. Through this fellowship, I will be hosted at the Colorado Public Utilities Commission. And with them, I will be helping them to understand a variety of different economic issues which are related to integration of solar on the grid and distributed energy resources. This fellowship is really exciting for me because I can apply academic and theoretical research to real world projects, and it will have real world implications. And I will discuss some of the topics we will be doing research on in the next few slides. So one topic we will be looking at with the Colorado PUC is to evaluate mechanisms which can help attribute resource adequacy and capacity accreditation levels to hybrid projects, that is solar plus storage projects. So typically, economic planning for electricity grids with high levels of renewables is done is done for capacity, is done to minimize outage probability and to meet peak demand. However, with increasing renewables on the grid, it is important to account for their shifting technology characteristics. So to account for the variability introduced by renewables on the grid planning needs to be more dynamic. Capacity accreditation methods that are typically used for solar and energy storage projects, they are developed separately and they don't really interact with each other. So there is a need for methodology which can help these factors interact, and so that is what my research will be focused on. I will be looking at the understanding. I will be looking at understanding the resource adequacy implications of hybrid projects in particular. A framework which is used typically in financial literature is value at risk or conditional value at risk. This framework is not typically used for resource planning, but it can help us understand what the risk of adding all these renewable technologies on the grid is, especially considering their variability on the grid. And more practically, we will be comparing evaluation of projects using the typical methodology and this new methodology. Another topic we will be doing research on is the economic efficiency of project siting. So it's important to understand what the key determinants of project siting decisions are, and especially using the energy equity lens. So basically trying to understand how energy equity issues can be considered while siting projects in an economically efficient way. This issue has been playing out in a number of ways in the current energy transition. One case of this is evaluating compensation mechanisms for communities where coal plants are retiring. What is the most economically efficient way to compensate such communities? Would it be through siting another renewable energy project in their place? Would that be economically efficient, or would compensation be better using another mechanism, say direct payments. However, that might not really be legally or politically viable. So our research will focus on understanding what the costs, benefits, and trade-offs are for these different kind of compensation mechanisms. So using the economic and policy analysis tools, particularly the econometric methods and optimization modeling methods I've learned in the Mineral and Energy Economics program. I have also conducted research on some of these other topics. I'm happy to talk about these in more detail if someone wants to. Some of these are my dissertation topics, but I won't really get into the details of these right now, considering we have only 5 minutes each. Thank you. And with that, I'll hand over to the next participant, to the next panelist.
All right, sorry about that. When I took control of the screen, all of my other controls went away. Anyway, my name is Daniel Cooley. I'm a PhD student here at the Colorado School of Mines, and I'm just going to talk a little bit about some of the more interesting bits of my research that I'm doing now with Dr. Smith. So, I'm looking at ways to apply deep learning in economics. If you don't know, deep learning is a field of machine learning that deals with artificial neural networks. So it's models that learn by doing, basically. They're generally used to perform classification tasks, and what I'm most interested in is the object identification portion of deep learning. And I think that it's pretty important for economists to start looking at things like this because they can provide really valuable data for economic analyses. And a lot of that data is going to be previously unexplored. And also a lot of the models that we use in deep learning are free and open source, and so they're really easy to access. One of the applications that I am using deep learning for is identifying center pivot irrigation systems. I took a model that was trained using manually identified center pivot irrigation systems in Nebraska and put it to work identifying CPIS over the entirety of the Ogallala Aquifer using satellite imagery. The model did a pretty good job. So comparing it against the manually identified CPIS, it had an accuracy rate of 99%. And a lot of the loss in accuracy is because it's not able to distinguish the boundaries like you see here, where the red is what my model predicted for the CPIS location, and the yellow is where the actual location is. So the model's it's pretty good at identifying where the CPIS is, but it's not very good at identifying where the boundary is. But the results are pretty trustworthy. This is a 1,000 kilometer by 1,000 kilometer sample of the results. And you can see that on the left with the manually identified center pivots, that it looks almost identical to my model's output on the right. It would take you a long time to probably find the 80-ish center pivots that the model didn't find when looking at these pictures. So the final product kind of looks like this. It's a raster that shows the predicted location of all of the center pivots over the Ogallala Aquifer. This map here shows it in blue. And I'm particularly interested in center pivots because of their unique properties as an irrigation technology. So using that, the output from that deep learning model in economic analysis is interesting because center pivots have a unique footprint that distinguishes them from other forms of irrigation. So they make circles around the central portion of it, as you might expect from the name. And so it leaves the corners of plots of lands unirrigated, which is something that you don't see with a lot of other forms of irrigation where it's like sprinkler irrigation or drip irrigation or something like that. Center pivots are also economically distinct from other forms of irrigation technology when examining things like farm value and crop value, which you can see here. We have a significantly positive relationship between the share of land in the Ogallala that has center pivots on it, between the farm value and the center pivot share, and also the crop value and the center pivot share. And then you can also see that center pivots provide greater crop resilience to unfavorable weather. So when the temperatures are higher or the precipitation is lower in an area, center pivots tend to do a better job than other types of irrigation, but they're not statistically different from other forms of irrigation. So more specifically using this, I am working on a paper with Dr. Smith that is kind of looking at the co-location of wind resources and center pivot irrigation systems. So on the left-hand side over here, these darker blue areas are where the highest wind power potential is in the United States. And this outlined area here is the Ogallala Aquifer. So as you can see, there's a lot of wind power potential over the Ogallala. But in figure 6, we see that wind turbines aren't actually being built in the interior of the Ogallala, where we see some of this higher wind power potential. And if you remember from a couple of slides ago, there's also a lot of center pivots in this centralmost portion of the Ogallala. And then you can see here that and these little light blue triangles here are identified wind turbines, and they tend to kind of avoid the center pivots. And where they don't, they are on the corners of the plots of land. So there's some kind of interesting spatial relationship between where you choose to put your wind farm and then where you choose to put your wind turbine within that wind farm if there's irrigation around like center pivot irrigation systems. And then using the deep learning models output, we can actually quantify the trade-offs between wind energy production and agricultural production, and look at things like setback rules as well. And lastly, you can also use these deep learning models to look at things from a dynamic perspective. So here on the right, I have a map of center pivot irrigation systems from 1988 to 2012. And I'm actually looking at Illinois here instead of the Ogallala Aquifer, but I'm only looking at it during significant drought years. So the blue portion is center pivots that were first identified in 1988. And then the red portion is 2005, and the yellow portion is 2012. And so using this model, we can identify these center pivots and kind of look at how they've been adopted through time and look at their influence on things like crop choices, crop yields, insurance payouts in drought years, and expansion of cropland. There's a lot of other things that you can use the deep learning models for as well. It doesn't have to be center pivot irrigation systems, but that is just kind of one of the applications that I am using it for currently. And then with that, I will hand it over to Use.
Hey, sorry, I was having a little bit of issue. Hi. My name is Jus. I'm a PhD candidate in mineral and energy economics, and I'm also doing some work in operations research with engineering. So here's a list of my research topics. The first chapter is an optimization model, and the first chapter only deals with developing the model and making sure that the model can actually provide a solution in a reasonable amount of time. The second chapter is built off on the first chapter, and it explores a case study in South Africa. And the goal of this model is to actually highlight the benefit of using renewable energy systems and different other energy technologies in South Africa. And the third chapter is not an optimization model, but it uses a statistical model to determine to study substitution in batteries that are used for electric vehicles. And we're currently developing a probit model to assess how different experts are ranking different determinants of substitution and how those rankings can differ based on the experts' affiliations, years of experience, and many other factors. I will talk about my second chapter, which is a case study that we're doing in South Africa. And so we are interested in South Africa because the country currently lives in a crisis of power supply. So what this means is that many different energy users, so we're talking about firms, households, and hospitals, are experience very frequent and short power outages. So if you look at South Africa in 2019, the country experienced about 15 outages per year. And this, if you do the calculations, you find that each outage lasted about 3 hours on average. We are particularly interested in studying hospitals, and that's because they also experience unreliable power supply. And there was a study that showed that only 34% of hospitals in 11 sub-Saharan African countries only had reliable electricity, which means continuous availability of supply. And the reason why we're also interested in studying this problem is because in an event of an outage, hospitals want to remain operational, so they invest in a backup generator. And the reason is that they want to keep providing power so that as a response to those outages, because we know that many hospital services such as refrigerations or surgeries require reliable electricity. So any outage, even lasting for a few minutes, can actually impose serious health risk. However, investing in a backup generator comes with a lot of challenges, and the reason is that the system is attributed to a lot of greenhouse gas emissions. And also the way the generator is designed is based on a rule of thumb instead of like an optimization model, and that can result in insufficient capacity. And the system is also fails to use different types of technologies. Another reason why we are investigating hospitals because hospitals have high cooling and heating needs, which some of the technologies that are employed in this model can actually meet. So this is the problem statement. This is a hospital in South Africa. As for the business as usual case, the hospital buys electricity from the grid. And in the event of an outage, the hospital invests in a backup generator. We assume that there is an on-site electric chiller to meet the cooling demand, and there's also an on-site boiler to meet the heating demand. So our question is, if given these multiple other technologies that a hospital has an option to invest in, how should these technologies be designed and how should they be dispatched so that the hospital can minimize energy cost. So we've developed a model in the first chapter that is being used to explore this case study in the second chapter. And the main important points is that the model output the system sizes for those different technologies. And it also output the different dispatch decision, when should these technologies be used. The model can also tell you how much would a hospital buy from the grid given these other technologies that are available. And the objective of the model is to minimize cost, and we do include a lot of constraints that the hospital face in making these decisions. So at this stage, we have completed a data set, but haven't gotten to the results yet. But this is an example of what we want to show. So in the end, we want to show PV, what would be the system size for this hospital that this hospital should rely on. But most importantly, you want to show the dispatch decisions. You have a whole week of dispatch. So this is from Sunday to Saturday. And the model shows you that in order to meet the demand, this is electricity demand, which is the solid line. For example, if you pick a Tuesday here, in order to meet the demand, the model decides to dispatch the CHP, the combined heat and power, and also PV, as well as the battery, but it only shows you that you need to buy this much from the grid. Whereas before you would have bought this much from the grid. So this is showing the, this model is showing the reduction of the dependency of the grid, which is actually crucial in environments like South Africa, where the grid is unreliable. So we will also intend to show the dispatch decision for the heating demand and also for the cooling demand. So as what we are currently doing right now, I need to conduct a sensitivity analysis. What cost makes sense for this hospital in South Africa? And also continue to assess those dispatch decisions that I just showed in the previous slide. And then also, we want to demonstrate the impact of using this optimization model. So we would take different rules of thumb that are used by this hospital to size these systems and compare them with the optimization model and then show the savings. And then later on, we will also pinpoint the policy decisions that are needed. Thank you. I will pass on to Hannah.
Hi, my name is Hannah Cayman. I'm a PhD candidate in the Mineral and Energy Economics Department at Mines. I'm going to be talking about some research that I've been working on in conjunction with Dr. Carbone, who you heard from earlier. The research is connected to a larger grant that's concerned with understanding the benefits of trade using a linked hydrologic and institutional as well as economic approach. Our research today and so far focuses on the externality effect of return flows in a water trading system. So the question we're trying to answer is, if users trade water naive to return flows from users upstream, does the trade outcome differ from the optimal allocation that's possible within that system? So return flows are a water that gets returned to the stream channel after a user diverts a certain volume of water. And we'll talk about a little bit about how that might result in an externality in the next slide. Great, so a little bit of background. Many of you are aware, regions in the Western US are becoming more and more water scarce. This is due to both pressures from migration, population migration, as well as climate change. And I guess motivating the reason why we're even looking at water trade as a policy is that economists typically prescribe a market-based policy to allocate scarce resources over rigid allocations, which actually result in most regions in the Western US that use the prior appropriation doctrine, which means that water gets allocated based on the first to use to the stream channel to start using that water for a beneficial use. And that doesn't necessarily align with the highest value use of that water. But still, calculating the gains from water trade remains a pretty active area of research. This is because there are a few factors that are specific to water that might change the way we measure the we might measure the surplus relative to the traditional economic theory of this. So we usually think that when we can equate users' willingness to pay for water, we achieve some amount of surplus. But things like high transaction costs or environmental externalities due to from water trade might make this gain, the surplus gain from trade, smaller. So we choose to focus on one specific factor in water trade, which we call return flow externality, which we think might alter the aggregate gain from water trade relative to an optimal solution that's possible within our simulated economy. So what I mean by an externality is any transfer where the parties involved do not fully internalize the effect of their transaction. So specific to return flow, this might happen if a user trades water upstream, not fully aware of the either decreased flow that a user in between them and their upstream water recipient might face, or the return flow that might be coming down to them at a later date. So this would result in them trading either a inefficiently low or high amount of water compared to what might be optimal. So the approach we take to measure the size of this externality is by linking CRAM and CG models. So CRAM is a water allocation model that we work with with folks at Linker Technologies. And this model is capable of utilizing many different institutional as well as hydrologic constraints in the way that it allocates water. And these serve as inputs into our computable general equilibrium model, which is well suited for this question because it's able to measure the behavioral responses of different sectors when they're faced with a change in their water allocation. So like I said before, CRAM generates water allocations under 4 different scenarios that we've deemed important just based on how their results might generate interesting research conclusions. So we change the scenarios by total inflow, which sector we're considering high value, and each sector's location along the stream channel. So we're then able to compute these allocations under how these allocations affect total GRP using our computable general equilibrium model, in which we calculate sector responses to their inputs based on production functions we've assigned to each sector that utilize water and labor as inputs. And output from this model results in total economy-wide GRP as well as sector-specific GRP. So these are some results that indicate the trade and maximum solution comparisons for each of our scenarios. And the X and Y axes here show the simulated output from each sector under each different water allocation scenario. Sorry, water allocation within a scenario. And each series represents one of the scenarios we've simulated. So in each chart, the orange series represents when the high value sector is upstream, and the blue series represents when the low value sector is downstream. And this changes within our each of our scenarios, and the leftmost chart is when we've assigned industry as the high value sector and ag as a high value sector on the right. So an important takeaway from these charts is that when the high value sector is upstream, the trade and optimal solutions indicated by the red and black lines respectively, or sorry, the red indicates the maximum GRP solution, and trade indicates the, and the black line indicates the trade solution. So these allocations align when the high value sector is upstream. This makes sense because the high value sector in the trade equilibrium will buy up most of the water. And this is also optimal because the upstream sector has the return flow. So we'll get kind of this optimal amount of water that can be used in the system where we're generating the maximum amount of return flow that the downstream sector can use. So these solutions diverge when the high willingness to pay sector is downstream. Again, this is pretty intuitive because the downstream sector buys up most of the water like before, but it actually would be optimal for more water to be allocated to the upstream sector. This is because it's true that the downstream sector does lose some output, but this loss is ameliorated by the return flow from the upstream sector, which more than outweighs the gain that the upstream sector receives due to an increased water supply. And these results are mirrored when we assign the high willingness to pay to the agricultural sector. So another interesting result from this initial analysis is that the size of the externality as measured by the difference between the light gray and dark gray bars in each chart is larger when we have agriculture as a high willingness to pay industry, and this industry is downstream. I should also say that these charts represent the relative decrease in total economic output from our benchmark scenario, which is why the numbers are all negative. And so, for example, this result right here matches the on the leftmost group on the leftmost chart matches the result in the bar graph and in the line charts we saw earlier, where when industry is the high willingness to pay sector and they're also upstream, the trade and optimal solutions align. They diverge when the low willingness to pay sector is upstream. And in the case when ag is a high willingness to pay sector, they diverge even more. This is because the opportunity that agriculture stood to gain from trading more water upstream is even higher due to the higher return flow coming from industry. Great, so that's those are all the slides I've prepared. I believe I am the last presenter, but I'd just like to say thank you and hand it off to our any concluding remarks.
So thank you, Hannah, and thank you to everyone else. We do have a few minutes for some questions. And I think probably the easiest way to do it is if you put your hand up. I'd be happy to turn on your microphone and you can ask your question out loud, or if you have any comments to make for any of the presenters. Or you can type in the chat, or you can type in the questions. Whatever works best for you. I had to give a presentation recently to the about research in economics and business, and I'm just always so excited to hear what people are working on and know the kind of the breadth and the depth of research in economics and business, both from our faculty and our students. We even heard about a little bit of undergraduate research that's going on. So happy to hear any questions. Right, I'm always the one who lets time go by in class. Make sure students have a chance to say something. But if there aren't any questions or other things, we'll post a recording of the session we had today. Thank you so much to all of our panelists, and thank you so much to all of you who joined us as attendees. And we'll do another alumni chat in the spring, and you'll get a notice of that. We'll try to mix in some of our innovations and reports on our academic programs, but also feature some of the research that's going on in the department. So thanks to all of you panelists, thanks to all of you who came tonight, and I hope you have a good evening.